Have you ever stopped to wonder about the silent, invisible architect dwelling within every piece of technology you own? What if I told you that a battle of ideas, a ghost story of design philosophies fought over 80 years ago, is the real reason your smartphone can stream a movie, your laptop can design a skyscraper, and your watch can track your very heartbeat? It's a story not of silicon and circuits, but of pure thought, a tale of how we taught sand to think, and in doing so, reshaped our world. This isn't just a history of computers, it's the secret blueprint of modern reality. And by the end of our journey, you'll never look at that glowing screen the same way again. Our story begins in the smoldering aftermath of World War II, a time of unprecedented innovation born from global conflict. In the hallowed halls of Princeton's Institute for Advanced Study, a Hungarian-American polymath named John von Neumann, a man whose mind danced effortlessly between quantum mechanics and game theory, penned a memo that would become the genesis of virtually every computer we use today. It was called the first draft of a report on the EDVAC, and it laid out a deceptively simple, yet monumentally influential, design, the von Neumann architecture. Imagine a master chef working in a tiny, one-room kitchen. This kitchen has a single counter where they must lay out their recipe book, the instructions, and their ingredients, the data. To cook, the chef first has to read a step from the recipe book, then put the book down, clear the counter, grab the ingredients, perform the step, clear the counter again, and then pick the recipe book back up to read the next instruction. It's slow, it's cumbersome, and every single action has to wait its turn. This, in a nutshell, is the von Neumann architecture. It proposed a unified memory space, a single reservoir where the computer stores both its to-do lists, the program instructions, and the stuff it needs to work on the data. The central processing unit, or CPU, the brain of the operation, communicates with this memory through a single, shared pathway, a data bus. Think of it as a single narrow hallway connecting the brain to its library of knowledge. The CPU has to run down this hallway to fetch an instruction, run back to decode it, then run down the same hallway again to grab the data needed for that instruction, and then run back to execute it. This constant, sequential back and forth created a fundamental traffic jam, a problem so persistent it earned its own legendary name, the von Neumann bottleneck. The processor, a marvel of speed and potential, found itself perpetually waiting. It was like a world-class sprinter forced to run a race through a revolving door. The bus could only carry one thing at a time, either an instruction or a piece of data, never both. Performance was forever tethered to the speed of this single, overworked pathway. Yet, we must not be too harsh on this design. Its sheer elegance and simplicity were its genius. In an era where building computers required rooms full of vacuum tubes and miles of wiring, simplicity was survival. Having one memory system was far easier and cheaper to design, build, and manage than any alternative. It democratized the very idea of computing, making the stored program computer a practical reality. Every laptop, every server, every smartphone you see today carries the DNA of this 75-year-old concept. It was the foundational compromise, the original sin of computing that made everything else possible. It was a flawed masterpiece, a bottleneck titan, and its limitations would become the driving force for every single innovation that followed. The quest to overcome this single, brilliant mistake would ignite a revolution. As the limitations of the von Neumann model became painfully clear, engineers and thinkers began to ask a radical question: what if the chef had to separate counters? One permanently dedicated to the recipe book and another just for ingredients? This simple yet profound idea gave birth to our second architectural philosophy, the Harvard architecture. Conceived around the same time but initially implemented in the Harvard Mark I computer, this design represented a fundamental schism in thinking. It boldly declared that instructions and data were not the same and shouldn't be treated as such. It physically separated the memory into two distinct banks, each with its own independent, dedicated bus connecting it to the CPU. Suddenly, the single, congested hallway of the von Neumann design was replaced by a two-lane superhighway. While the CPU was using one lane to drive back from memory with a new piece of data, it could simultaneously use the other lane to fetch the next instruction in the program. There was no more waiting. The fetching, decoding, and data accessing phases of a command could overlap, allowing the processor to work in a continuous, fluid rhythm. This parallelism, this ability to do two critical things at once, resulted in a dramatic boost in throughput and performance. This architectural purity made the Harvard model a natural fit for specialized applications where speed and predictability were paramount. Think of a microcontroller in your car's anti-lock braking system. It needs to read sensor data and execute precise instructions in a fixed, unchangeable rhythm. There can be no delays, no waiting for a shared bus. The Harvard architecture's deterministic nature knowing and instruction fetch will never be delayed by a data transfer made it the gold standard for real-time embedded systems. Digital signal processors DSPs that handle our audio and video and the tiny efficient brains inside our Wi-Fi routers and microwaves. However, this purity came at a cost. Building and managing two separate memory systems was more complex and expensive. The design was less flexible. For example, it was much harder for a program to modify itself, a practice that, while rare today, was an area of early computer science research. This is why a fascinating compromise emerged in the modern era. The computer on your desk right now is a hybrid of these two warring ideas. At its core, it still uses a unified main memory RAM like a von Neumann machine for cost and flexibility. But look closer inside the CPU itself, and you'll find the ghost of Harvard. The CPU's cache is small. Lightning-fast pockets of memory are often split into an L1 instruction cache and an L1 data cache. This creates a tiny internal Harvard architecture, giving the processor the best of both worlds, the parallel fetching speed of Harvard for its most immediate tasks, and the flexibility and scale of von Neumann for its larger memory pool. It's a beautiful testament to how great ideas in engineering don't die, they simply find new ways to coexist. As the hardware world was splitting over memory design, another debate was raging, this one about the very language of the processors themselves. How should a CPU understand our commands? The first dominant answer to this question was CISC, which stands for Complex Instruction Set Computing. And if you want to understand CISC, you must first understand the world in which it was born, a world where memory was not just a component, but a precious, outrageously expensive commodity. Imagine paying for every single word you wrote down. You'd quickly learn to be concise. You wouldn't write, "Pick up the apple," then slice the apple, then place the apple in the bowl. You'd invent a single, powerful word, "prepare apple." This was the core philosophy of CISC. Programmers in the 1960s and 70s were writing in low-level assembly language, and memory was sold by the kilobyte at prices that would make a modern billionaire weep. The goal was to make programs as compact as possible, to reduce the number of lines of code needed to accomplish a task, thereby saving precious memory space. CISC processors were designed to be fluent in these powerful, multi-layered commands. A single CISC instruction could trigger a cascade of operations. For example, a command like mult might not just multiply two numbers. It might first load one number from a specific memory address, load another number from a different address, multiply them together, and then store the result back into memory, all in one go. It was the prepare apple instruction in silicon form. To achieve this, CISC designers used a clever trick called microcode. Each complex instruction wasn't hardwired into the processor's logic. Instead, when the CPU received a command like mult, it looked it up in a hidden, internal rulebook or read-only memory containing tiny, elementary instructions called microcode. This microcode would then guide the hardware, step by step, through the multiple actions required. This approach was brilliant because it allowed designers to add new, complex instructions without having to redesign the entire processor. They just had to update the microcode rulebook. The undisputed king of the CISC world is the x86 architecture. the powerhouse behind virtually every desktop and laptop computer for the past 4 decades, from Intel's earliest 8086 processors to the Core i9 of today. Its success was driven by a commitment to backward compatibility. Each new generation of x86 processor could run the software of its predecessors, creating a powerful ecosystem that developers and businesses could rely on. But this complexity was a double-edged sword. Like a Baroque masterpiece, CISC was ornate and powerful, but also incredibly intricate. Those multi-part instructions took varying numbers of clock cycles to complete, making it difficult to optimize performance and create efficient pipelines. The complex hardware required more transistors and consumed more power. The microcode translation layer added a small but significant overhead to every single command. The very thing that made CISC great, its rich, expressive vocabulary, was also becoming its greatest liability. The stage was set for a rebellion, a call for a return to simplicity. The rebellion arrived in the early 1980s, and it was called RISC, for Reduced Instruction Set Computing. It was a philosophy born from a simple, yet revolutionary, observation by researchers at IBM, Stanford, and Berkeley. They analyzed the code that CISC computers were actually running and discovered a startling truth. The vast majority of the time, those fancy, complex, all-in-one instructions were being ignored. Compilers, the software that translates human-readable code into machine instructions, were consistently opting to use simpler, faster, more basic commands. The CISC approach of Prepare Apple was being overlooked in favor of a sequence of get knife, pick dash up dash apple, cut apple. Why? Because it was easier for compilers to optimize a series of simple, predictable steps than one monolithic, opaque command. The RISC philosophy took this observation and turned it into a design creed. It was the architectural equivalent of a Spartan warrior, stripped down, brutally efficient, and focused on one thing: speed. RISC throughout the complex, multi-cycle instructions and the microcode translation layer. In their place, it established a small, highly optimized set of instructions that were all the same size and, crucially, designed to be executed in a single clock cycle. This simplicity had profound consequences. Instead of one instruction taking, say, 5 or 10 clock cycles, and another taking 2, every RISC instruction took just 1. This uniformity made it incredibly easy to implement a technique called pipelining. Imagine an automotive assembly line. Car number 1 is getting its wheels, car number 2 is getting its engine, car number 3 is getting its chassis painted, and car number 4 is having its frame welded. For cars are being worked on simultaneously, each at a different stage. This is pipelining. By breaking down the process of executing an instruction into simple, uniform stages: fetch, decode, execute, write back, a RISC processor could have multiple instructions in its pipeline at once, finishing one instruction on every single tick of its clock. It was a torrent of relentless, high-speed execution. RISC also championed a load-store architecture. The only instructions that could access memory were explicit load and store commands. All other operations, like addition or multiplication, had to be performed on data that was already brought into the CPU's registers at small, super-fast internal scratch pads. This minimized the slow trips to main memory, keeping the action inside the fast-beating heart of the processor. The success of this philosophy has been nothing short of staggering. Architectures like MIPS and SPARC found homes in high-performance workstations and servers. But the undisputed global champion of RISC is ARM. Originally from the UK, ARM designs became the blueprint for the processors in over 95% of the world as smartphones and tablets. Their simplicity, efficiency, and low power consumption made them perfect for battery-powered devices. Apple's groundbreaking M-series chips, which have redefined performance and efficiency in laptops, are built on the ARM RISC architecture. Over time, the lines between CISC and RISC have blurred into a fascinating gray area. To compete, CISC processors like Intel's x86 began to adopt RISC-like features internally. When your modern Intel CPU receives a complex CISC instruction, its first step is to break it down into simple, RISC-like micro-operations, which are then fed into a highly pipelined, Superscalar execution core. Meanwhile, RISC designs have gradually added more instructions to their set to handle specific tasks more efficiently. The two great rivals, once philosophical opposites, have learned from each other, borrowing the best ideas in their relentless pursuit of performance. As the CISC versus RISC debate matured, a new and ambitious idea emerged, one that sought to transcend the limitations of both. It was called EPIC for explicitly parallel instruction computing. This architecture wasn't just an evolution. It was a gamble, a bet that the smartest thing in the room wasn't the hardware, but the software. To understand EPIC, we must first understand the problem it was trying to solve: instruction-level parallelism. Both CISC and RISC processors were spending an enormous amount of energy and silicon on complex hardware designed to look ahead in the code, identify instructions that could be run in parallel without interfering with each other, and then schedule them on the fly. This was a monumental task, like a traffic controller at a chaotic intersection trying to figure out which cars can go at the same time without crashing. EPIC's radical proposal was, what if we could get rid of the traffic controller? What if the route was planned out perfectly in advance? The EPIC philosophy shifted the immense burden of finding and scheduling parallel instructions from the processor as hardware to the compiler. The compiler, with its godlike view of the entire program, would act as an oracle. It would analyze the code, identify which instructions were independent, and then explicitly bundle them together into packets. It would essentially hand the processor a perfect, pre-chewed, pre-digested plan, saying, here, these 3 instructions are safe to execute at the exact same time. No need to check, I've already done the work for you. This was VLIW, very long instruction word on steroids. But EPIC added several clever enhancements to make this prophecy more reliable. It introduced predication, a way to eliminate unpredictable branches if-then statements in the code. Instead of guessing which path a program would take, the processor would execute the instructions for both paths, and a predicate bit in the instruction would tell the hardware which result to keep and which to discard. It was like exploring 2 parallel universes simultaneously and then simply choosing the one that mattered. EPIC also introduced speculative loading, allowing the compiler to schedule a load instruction to fetch data from memory long before it was actually needed, hiding the long latency of memory access. The flagship implementation of this bold vision was Intel's Titanium processor. It was a joint venture with Hewlett-Packard, and for a time, it was hailed as the future of high-end computing. The inevitable successor to x86, it was a marvel of engineering, a processor built on the belief in the power of intelligent software. But the Oracle's prophecy failed. Titanium and the EPIC architecture ultimately struggled to gain widespread adoption for several critical reasons. The first was the immense complexity of the compilers. Writing a compiler that could effectively analyze and bundle instructions for a real-world, messy program proved to be astronomically difficult. The Oracle was often fallible. Second, this created a chicken-and-egg problem. Without a large software base compiled specifically for Titanium, there was no reason for customers to buy the hardware. But without the hardware in people's hands, there was no incentive for developers to invest in building the complex compilers and porting their software. Finally, the relentless, incremental improvements in the dumber x86 hardware, which continued to throw more transistors at the problem of on-the-fly scheduling, proved to be good enough and, crucially, maintained backward compatibility with decades of existing software. While Titanium may be considered a commercial failure, its ghost haunts modern CPU design. The ideas of speculation, predication, and compiler-driven optimization have been absorbed into the broader world of processor architecture. EPIC was a beautiful, daring dream of a future where software and hardware worked in perfect, preordained harmony. It may have been a dream that came too soon, but its echoes helped shape the waking world. While Epic bet on the compiler, another design philosophy was perfecting the art of hardware-level magic. This was the Superscalar architecture, and it didn't just build a single assembly line for instructions. It built multiple, parallel assembly lines and then hired a master juggler to keep them all busy. The core idea of a Superscalar processor to execute more than one instruction per clock cycle. If a RISC pipeline was an assembly line finishing 1 car per hour, a Superscalar processor was a factory with parallel assembly lines, aiming to finish 4 cars every hour. To do this, it duplicated key parts of the processor's internals, the execution units. It might have multiple integer units, multiple floating point units, and multiple memory access units, all standing ready to work in parallel. But simply having more hardware isn't enough. The real genius of the Superscalar design lies in the incredibly sophisticated logic that feeds these units. This is where the magic happens, primarily through a process called out-of-order execution. Imagine you have a simple to-do list: wash the car, wait for the car to dry, mow the lawn, put the dry car in the garage. A simple pipelined processor would execute these in order. It would wash the car, then sit idle, waiting for it to dry. Only then would it move on to mowing the lawn. What a waste of time! A Superscalar processor with out-of-order execution is much smarter. Its advanced scheduling logic would look at the list and see that mowing the lawn instruction 3 has absolutely no dependency on washing the car instruction 1 or it drying instruction 2. So while the processor is waiting for the car to dry, it dispatches the lawn mowing instruction to a free execution unit. It executes instructions based on their readiness, not their original order in the program. Once the car is finally dry, it executes instruction 4. The result is the same, but the total time taken is drastically reduced. To make this juggling act possible, Superscalar CPUs employ a host of mind-bending techniques. Branch prediction is a crystal ball that tries to guess the outcome of an if-then statement far in advance, speculatively executing instructions down the predicted path. If it guesses right, it has saved a huge amount of time. If it guesses wrong, it flushes the pipeline and starts over, but sophisticated predictors are right over 90% of the time. Register renaming is a clever shell game that eliminates false dependencies, creating temporary, shadow registers to allow instructions that happen to use the same register name but don't actually depend on each other's results to execute in parallel. This architecture became the bedrock of virtually all modern high-performance processors, from Intel's Core series to AMD's Ryzen and Apple's M series. It is the engine that extracts hidden parallelism from the single-threaded, sequential code that makes up most of our software. For decades, the path to faster computers was to make this Superscalar engine wider, more execution units, and smarter, better prediction and scheduling logic. But this path eventually led to a wall. The amount of instruction-level parallelism that can be extracted from a typical program is finite, making the Superscalar engine ever wider yielded diminishing returns. Furthermore, the complex logic required to manage this out-of-order chaos consumed enormous amounts of power and generated a tremendous amount of heat. The quest for single-core performance had reached its physical limits. A new kind of parallelism was needed. For decades, the drumbeat of progress in computing was the steady, intoxicating rhythm of rising clock speeds. Every 18 months, it seemed, processors got twice as fast, a phenomenon enshrined in Moore's law. But in the early 2000s, that drumbeat began to falter. The party was over. Pushing clock speeds higher and higher had run into two fundamental laws of physics: the power wall and the heat wall. Cranking up the frequency of a chip increases its power consumption and heat generation exponentially. Processors were threatening to melt themselves. The race for raw speed was over, and the race for efficiency had begun. The solution was as elegant as it was transformative. If you can't make one core faster, then use more than one core. This was the birth of the multi-core architecture. Instead of a single, monolithic, incredibly complex and hot-running processor, manufacturers began placing 2, then 4, then 8 or more complete, independent processor cores onto a single piece of silicon. Each core was its own brain, with its own pipeline and execution units. It was a shift from building a single, genius sprinter to building a team of very good marathon runners. This changed everything. A dual-core processor could, in theory, run to separate tasks, say, a web browser and a word processor simultaneously, without either one slowing the other down. The operating system, the master conductor of the computer, learned to become a task scheduler, intelligently assigning different software threads to different cores. This is why your modern computer feels so responsive. Even when one program is working hard, other cores are free to handle the user interface and background tasks. The concept was then scaled up dramatically to create many-core processors, like those found in high-end servers and GPU's graphics processing units. A modern GPU isn't just a multi-core chip. It's a many-core monster with thousands of small, relatively simple cores designed to perform the same operation on massive amounts of data in parallel. This is why GPUs are perfect for the repetitive, parallelizable math of 3D graphics, scientific simulations, and, most recently, the training of artificial intelligence models. However, this new paradigm came with a critical catch, often summarized by the phrase, "the free lunch is over." In the single-core era, software would automatically get faster when run on a new computer. With multi-core, this was no longer true. A piece of software written as a single, sequential series of instructions, a single thread, could only ever run on one core at a time. The other 7 cores on your octa-core CPU would sit completely idle, providing zero benefit. To unlock the power of the hive mind, software itself had to be rewritten to be parallel. Programmers now had to think like a project manager, breaking down a large task into smaller, independent subtasks that could be distributed among the available cores. This is a fundamentally harder way to program, fraught with new challenges like race conditions and synchronization issues. To wring even more efficiency out of each core, technologies like simultaneous multi-threading SMT, known as hyper-threading by Intel, were introduced. SMT allows a single physical core to present itself to the operating system as to virtual cores. It uses the inevitable small bubbles and stalls in one thread as pipeline to sneak in instructions from another thread, keeping the core's execution units busy more of the time. It's the ultimate form of efficiency, ensuring that no part of the precious silicon is left idle. Our story now arrives at its final, and perhaps most clever, chapter, the rise of the hybrid architecture. This latest evolution recognizes a simple truth about the way we use our devices. Not all tasks are created equal. Reading an email requires a tiny fraction of the processing power needed to edit a 4K video. So why use a sledgehammer to crack a nut? The hybrid architecture tackles this by combining different types of cores on a single chip. It builds a balanced team. On one side, you have the performance cores P cores. These are the big, powerful, superscalar beasts we've come to know and love. They are wide, complex, power-hungry, and designed for maximum single-threaded speed. They are the star athletes brought onto the field for the most demanding, performance-critical tasks. On the other side, you have the efficiency cores E cores. These are much smaller, simpler, and more power-efficient cores. They are designed to handle background tasks, notifications, and less demanding workloads with the absolute minimum energy consumption. They are the diligent, reliable support crew working behind the scenes. The pioneer of this concept in the mobile space was ARM's big, little technology. It paired powerful big cores with frugal little cores, and the operating system could seamlessly switch tasks between them. When you are scrolling through a web page, the little cores are doing the work, sipping battery. The moment you launch a demanding game, the task is instantly handed off to the big cores for a burst of speed. Apple took this concept and perfected it with their M-series silicon, and Intel has now brought it to the mainstream PC market with their latest core processors. A sophisticated hardware scheduler, working in concert with the operating system, acts as the team's coach. It analyzes the incoming workload in real time and dynamically assigns each thread to the most appropriate core. This intelligent delegation allows for a device that is both incredibly powerful when needed and incredibly efficient when it is not, revolutionizing battery life in laptops and thermal management in desktops. This hybrid idea is the culmination of our entire journey. It blends the raw power of complex superscalar designs with the efficiency-focused principles of simpler cores. It acknowledges the need for both high-intensity parallel processing and low-power background operation. It's not about one single design philosophy winning. It's about creating a diverse and adaptable system where different architectural ideas coexist and collaborate to handle the multifaceted demands of modern computing. From specialized AI accelerators and image processors to these P-core, E-core combinations, the future of CPU design is not monolithic. It is a mosaic. So, what have we learned from this 80-year journey through the soul of our machines? The story of computer architecture isn't just a technical history. It's a profound lesson in problem solving. It teaches us that progress is often born from fixing the elegant mistakes of the past. Von Neumann's beautiful, simple design gave us the computer, but its bottleneck forced generations of geniuses to invent new paths forward. It shows us that there is often no single right answer. The battle between CISC and RISC didn't end with a victor, but with a synthesis, a blending of the best ideas from both camps. It's a reminder that complexity and simplicity are both powerful tools, and wisdom lies in knowing when to use each. Most importantly, this story teaches us about the power of abstraction and specialization. From the single, overworked core to a hive mind of specialized P-cores and E-cores, the journey has been about breaking down a monolithic problem into smaller, manageable parts and assigning the right tool for each job. This is a lesson we can apply to our own lives. When faced with an overwhelming project or a complex problem, don't try to solve it with one massive, brute force effort. Break it down. What are the high-performance tasks that require your full, focused attention? And what are the low-energy background tasks you can handle more efficiently? By building your own hybrid architecture of focus and efficiency, you can achieve more with less stress and energy. This incredible, invisible ballet of competing ideas is happening billions of times per second inside the device you are using right now. It is a testament to human ingenuity, a story of how we wrestled with the laws of physics and logic to create something extraordinary. So I leave you with this to ponder. As we move into an age of quantum computing and neuromorphic chips that mimic the human brain, what new architectural original sign are we creating today? What brilliant, flawed idea will future generations strive to overcome? Let me know your thoughts in the comments below. What part of this journey surprised you the most? Thank you so much for joining me on this deep dive today. I hope this has demystified the inner world of your computer. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.